Hey everybody, welcome to this next video lesson where we're going to talk about how to use this new tool molar mass in order to do simple math problems. Did you notice that molar mass had two units? It had grams and moles, and because it has two units, it can be used as a conversion factor. You can use it to convert from moles if you know the grams, or you can convert it to grams if you know the moles. I have an example of each here. Take a look. This first question says, how many grams are there in 3.45 times 10 to the negative third moles of potassium nitrate? Now, first thing I need to know is the molar mass of potassium nitrate. So I pull out my periodic table and I figure out how many potassiums and how many nitrates there are in potassium nitrate. Well, potassium is a +1 charge and nitrate is a -1 charge, and so you just have one of each. Now, if I add up the numbers from the periodic table, you get potassium, which is 39.09, nitrogen, which is 14.01, and oxygen, which is 16, but I'm going to multiply that by 3. So the molar mass becomes 101.11 grams per mole. And if you noticed, I rounded this first number for potassium to 39.10 because if you look on the periodic table, it's actually 39.098. And as I mentioned before, I always round my molar masses to 2 past the decimal. So the molar mass of this molecule, potassium nitrate, is 101.11 grams per mole. Now, because I know the moles, I can set up a unit conversion, or in other words, a dimensional analysis problem, where the first number in the top is the number I'm given, 3.45 times 10 to the negative third moles. Now I have to match units from the top left to the bottom right. And what you get when you have the molar mass is that it's telling you there's 101.11 grams for every 1 mole of substance. So 1 mole goes in the bottom and 101.11 grams goes in the top. Now, since this is a fraction multiplied by a fraction, we just simply multiply the numerators and we get the final answer. Since there's no number in the denominator, it's just 1 times 1. So take this times this, and your final answer is 0.349 moles of KNO3. Now I used 3 significant figures in my final answer because the original number had 3 significant figures in it, and a molar mass, because these numbers are added up off the periodic table, do not count as significant values. Or in other words, they have infinite significant values. So my answer has to reflect the same number of significant values as that starting number that I had. So the correct answer is 0.349 moles of KNO3 rounded off. Now this is an example if you have moles and you're converting to grams. Now what if you have grams and you're converting to moles? Well, you can use molar mass again. This time I have magnesium chlorate. Magnesium chlorate's formula, well, magnesium is a +2 charge and chlorate is a -1 charge, so I need 2 chlorates for every 1 magnesium. Now, like I did before, I'm going to add up the molar masses of my different substances. Magnesium is 24.31. Now this time I have chlorate, but times 2, so that's 2 chlorines and 6 oxygens. So chlorine is 35.45 times 2, and oxygen once again is 16.00, but times 6, because you got 3 of them, times 2 is 6. And when you add all those up, you get a final answer of 191.21 grams per mole. Now I'm going to set up my dimensional analysis, and this time I'm going to put 2.23 grams of the magnesium chlorate in the upper left-hand corner over 1, and I'm going to use this molar mass again, but this time I want the mass, the 191.21 grams, to go on the bottom because I need grams to cancel grams. And I'm going to put 1 mole on top, and this time I'm going to divide these two numbers because they are diagonal from one another. If they're next to each other, they multiply, and if they're diagonal, they divide. So when you take these two numbers and divide them, you get an answer of 0.0117 rounded to 3 significant figures. Now once again, I'm going to use 3 significant figures because my first number was 3 sig figs. These numbers don't count as significant because they were added up off a periodic table. So my answer with proper label is 0.0117 moles of magnesium chlorate. And that is how you do problems that involve grams and moles in dimensional analysis using molar mass. Now the last slide we talked about how to relate mass and moles together, but how do you relate moles and moles of 2 different substances? The only way to do that is to call into our old friend the balanced chemical reaction. Now when we learn about balanced chemical reactions, we use these coefficients out in front of the reactants and the products, and those coefficients represented numbers of atoms or numbers of molecules that we use to balance the reaction. But as we talked about, chemists don't usually use individual atoms or molecules when we discuss chemical reactions. Rather, we take into account large quantities, which we now call a mole. So if these coefficients represent the number of atoms, they could also represent the number of moles. Because it's a 1 to 5 to 3 to 4 to molecule ratio, it can also be a mole to mole to mole to mole ratio. So in order to do mole to mole conversions, in other words, if I know the moles of one thing from a chemical reaction, I can convert to moles of another thing using these proportions. That's what they are. They're proportional. They're ratios. This is called the mole ratio. So no longer should you think about the numbers as coefficients, meaning individual molecules. You should consider them as moles of the substance instead. So I'm going to bring your attention to this first problem down here. It says if I have 4 moles of propane, well, how many moles of carbon dioxide can I produce? And you might be wondering, well, what about the oxygen and what about the water? Well, in problems like this, you can only compare 2 things at a time. Even though the chemical reaction might have 4 things in it, you only can compare what you know and what you're trying to find. And the other ones are just extra information, so we don't really worry about them. So we begin a dimensional analysis problem with 4 moles of propane in the upper left-hand corner. And it's important to label moles of what, because now we're going to do problems where we have moles compared to other moles. And if you just put moles instead of moles of propane, you might get it confused because we need the units to cancel by matching diagonally. And if you just have moles and moles, it might not be the right moles down here. So the top one should be moles of propane, or C3H8. Now I'm going to put moles of C3H8 down here in the bottom right so that they cancel each other out. And what I'm converting to is moles of CO2 in the upper right-hand corner. And all I need to do is take the coefficient numbers from the balanced chemical reaction and put them in here. So 3 for CO2 and 1 for the C3H8. Now, when I multiply these two together, 4 times 3 is 12. And the answer needs to be labeled moles of CO2 as to not be confused with moles of any other substance in this problem. Keeping in mind significant figures again, 4.0 is a measured value and the 0 is significant, so my answer can only reflect 2 significant figures. Once again, mole ratios are known values pulled from a balanced chemical reaction, so they don't count as significant. So my answer reflects the same precision as my first number. I can do the same thing for this bottom one. I'm going to set up my train tracks once again. I'm going to put 18 moles of water. How many moles of oxygen will be used? So this time I want moles of H2O on the bottom and moles of O2 on top because I'm converting to moles of oxygen. The balanced chemical reaction says that there's 5 moles of oxygen for every 4 moles of water. And when I do the math, I take 18 times 5 and divide by 4, and I get an answer of 22.5 moles of oxygen. And it's important, once again, to consider significant figures. There were 3 significant figures here, and there are 3 significant figures here, so my answer is finished. In summary, I showed you examples of how to use molar mass to be able to convert from moles to mass and mass to moles, and I also showed you how you can use a new tool, the balanced chemical reaction, in order to convert from moles of one substance to moles of another. And those 2 skills are going to be very important moving forward when we put it all together into multi-step stoichiometry type problems. Well, that takes care of this video lesson. Thanks for watching.